Sorry about that, guys. Apparently, I ran out of time on that video. But anyway, back to the expansion valve and/or capillary tube, whatever it may be. Basically, what this is more or less it's a metering valve or a gateway between the high pressure side and the low pressure side. So far we've been talking about the compressor, and the compressor is supposed to build up pressure, right? So everything beyond the compressor is going to be high pressure all the way to the condenser. We're going to have a state of change, matter change through the condenser, but it's still high pressure through the receiver dryer, high pressure all the way up to the thermal expansion valve and or capillary tube. Um, but anyway, uh, at this point, basically we have a very small metering orifice, and that orifice opening and closing is what creates um, a lower pressure on the output side because only a little bit is allowed to get through. So we end up with a very low pressure on the backside of this metering valve, which creates um, obviously a very big temperature differential. That's the effect because there's a different pressure differential on the outside, which would be the cause of the temperature differential. So anyways, we have the low pressure on the output side, which then goes into our um, evaporator right here, our evaporator core. In the evaporator core, we will have a state of matter change because it'll be absorbing the heat outside of the cab. And so as it absorbs that heat, it becomes a gas or a vapor. That gas or vapor then comes out of the evaporator, travels back to the compressor where it's recompressed as a high pressure gas or vapor, goes back into the condenser once again and goes through the condenser. We have a state of change from vapor to a liquid. That liquid is still under high pressure, goes through the receiver dryer and back to the expansion valve, and it repeats the process over and over and over and over. But that's pretty much the gist of it. The big thing is knowing that state of change and knowing the components along the way. This is just one style. There's an accumulator style as well. The accumulator works with the capillary tube. We're going to talk about that later, but just for now, for introduction, this is how far we're going to go. So let's move on. All right, so here's a little bit better explanation of that actually state of change and that matter change. So we have our compressor. There it is. Our compressor right here. That compressor builds the pressure. I always like starting at the compressor. The compressor and the H block are kind of my two favorite places to start when I'm talking about a system like this because they're the two opposite ends. We go from low pressure on the compressor to a high pressure on the compressor, whereas down at our H block or our expansion block, we go from a high pressure to a low pressure. So they're more or less the gateways or the doors in the system. So anyway, back to the compressor. Compressor takes a low pressure vapor or gas, turns it into a high pressure gas. That gas then goes through the condenser. Now the condenser, remember, is located in front of the radiator, so it's got ram air pushing through it. And that ram air, essentially, what it does is it causes the heat to be pulled out of the freon. Now when that heat's pulled out of the freon, we're going to get a state of matter change, right? It's going to go from a vapor to a liquid. Now, you're also going to get some temperature differential here, but the big deal, the main thing we want is the matter change to a liquid. So that liquid goes through a receiver dryer. This is a bunch of little desiccant balls inside of here. Desiccant absorbs moisture, water, which is a good thing, right? We don't want water in this system. Freon and water do not mix well. It causes a lot of corrosion real fast. So coming out of the receiver dryer, you got kind of more or less, it's like a gas liquid mixture coming out of the dryer. That gas liquid mixture travels through down to our H block. Got an itty bitty tiny little orifice right here that opens based upon the pressure on the back side. So as pressure changes back here, it opens and closes this little needle, which opens and closes the port right here. opening and shutting it off. So now all of a sudden, since this is such a small orifice and since it's only open part of the time, um, that what that creates is a low pressure on this back side. Now that low pressure is, once again, it's kind of a vapor, gas, liquid mixture, um, more than one state. And then it gets into the evaporator. Now the evaporator here is located inside the cab or just on the outside of the cab, something along those lines. And the air that is pushed through it is usually cab air. It could be cab air or it could be outside air, depending on what you have your knobs on your AC system set at, which is kind of interesting. I'd like to bring this up real quick. I like to ask this question in class, and so I'll probably ask it when we're talking Thursday or Friday. Um, but do you know what the difference is between a MACS AC and just an AC? That's set on high. So you obviously have your knobs to adjust how high your AC is, but then you have the little max button. And the difference between having that max button on or off determines where the air going through the blower is coming from. If it's coming from outside air or if it's coming from the air that's already inside the cab. Obviously, if it's already inside the cab, then it's going to be colder air going in, which means, once again, you're going to have even colder air coming out once it travels through the evaporator. But anyway, as that air is forced through the evaporator, the heat inside of the Freon, so any heat that's inside of here is going to be, or I'm sorry, excuse me, the heat that is inside the air, any heat that's inside the air as it travels through the evaporator is going to get pulled into the Freon. So it wants that heat because it's trying to go through, once again, a state of matter change. It's trying to go from a liquid vapor mixture to a pure gas. So as that state of change happens, it's pulling the heat out and creating a state of matter change, which is essentially the effect is cold air gets blown through the evaporator into the cab. So then that low pressure gas then travels through the backside of the H block in this case. That H block, once again, opens and closes the orifice, and then gets sucked into the compressor where it then closed system goes back through the whole system again. All right, so here's an example of kind of what the components look like once again with the states of change. So here's our compressor right here. Got our discharge side, so high pressure, under pressure side going through our condenser. We're going to have our state of change through the condenser. We now have a liquid, high pressure liquid moving through our receiver dryer, going up into our H block right here. That H block is then going through our evaporator. Well, once it goes through our H block, we have now low pressure. Goes through the evaporator, creates a low pressure gas, which then makes its way back to the compressor. Once again, I mean, I'm showing you tons of different diagrams showing the exact same thing over and over and over and over, but it's because you have to know it. You absolutely have to know this. The state that it's in and the temperature changes that it's going through because of the state that it's in is what an AC system is. So you got to get this figured out. High pressure liquid versus high pressure vapor versus low pressure liquid, low pressure vapor. That's an AC system. You have to be able to understand this. Otherwise, you're going to run into some issues. So if you have to back up and watch these again and again and again, whatever you have to do, you got to understand this. So once again, we have a compressor, stage one. Compressor builds the pressure. So you have a high pressure gas coming out of the compressor. As it reaches the condenser, our heat is pulled out of it. Remember, it's going through that latent heat removal. So it's becoming a liquid. Once it goes through the condenser, it goes into the expansion valve. The expansion valve has that itty bitty tiny orifice, so only some is allowed out on the backside. So you got a low pressure liquid on the outside. As it travels through the evaporator, heat is drawn into it, so our latent heat vaporization is coming in now. So our latent heat comes in, and our output is a low pressure gas. All right, refrigerant flow cycle. Last time, I promise. Whatever it takes, just you got to know it. Compressor, output, high pressure through the condenser. This is high pressure vapor, right? Um, Once it gets to the condenser, it's going to be a high pressure liquid through the receiver dryer. Out of the receiver dryer, you got, oh, it's more or less a vapor liquid mixture, but it's all under high pressure. High pressure gets into the expansion valve. Once it gets into the expansion valve, this one's a thermostatic expansion valve, not an H block. I'd like to show that real quick. So on this one, we have, here's our expansion valve. We got a little temperature sensor, more or less, coming down here, and it's reading the temperature on the backside of this evaporator. So as that temperature changes, it opens and closes the expansion valve, allowing more or less freon to travel through. On the backside, we have a low pressure liquid coming out. As it goes through the evaporator, it becomes a low pressure gas. And that low pressure gas goes to the compressor. Start the cycle over again. Last time, I promise. Hopefully you got it. Any of these times, whichever diagram works best for you, use that one. Doesn't really matter. All right, so refrigerant, the stuff inside of the AC line itself. Pretty important, right? Water technically could work. Its boiling points aren't really very good for an AC system, but it could work. If you were to change the pressures enough, it could technically do the job. Just about anything can. Anything that holds any sort of heat energy whatsoever, which anything above negative 460 degrees Fahrenheit, I believe, is the cutoff for heat energy. At negative 460 degrees Fahrenheit, you have no heat energy, but negative 459, it would still work for an AC system. Your boiling point would just be ridiculous. So, with that being said, refrigerant, pretty important, the different types of refrigerant, changes for the service that you're going to be using. Typically, anything you find on ag or over the road or anything industrial today is using the R134A. R134A, basically, it's still a greenhouse gas refrigerant, but it's not toxic. R12 was the older system. And that R12, basically, if you came into contact according to OSHA and EPA and everything, you were just going to die. I mean, that was the end of it. But the R134A, it's a little less toxic. It's a little bit better for ecosystem, but technically still a greenhouse gas, so they still don't like it a whole lot. But the main thing is the function of a refrigerant is it needs to absorb heat from the air in the cab. Then it needs to be able to transfer that heat to outside of the cab where it then can release the heat. And all of this, once again, is done through a state of matter change. But, you know, it's a little bit controversial in the last 5 years about what's the best refrigerant. So we'll get into that a little bit more. So until we're going to run out of time again before the video kicks me. We'll try to get through this one. Until 1995, the common refrigerant used in a truck AC system was known as R12. This is classified as a chlorofluorocarbon. R12 refrigerant boils at negative 22 degrees Fahrenheit. And for years, it was considered an ideal mobile vehicle AC refrigerant. However, because it is a substance of some toxicity as well as ozone depleting, its use has, in theory, become strictly controlled under the guidelines of Federal Clean Air Act. Well, we finished it because, well, basically, I've already told you all about that. There's nothing new that we haven't already talked about. So we'll move on to the next video. We'll move on to the next refrigerant and go from there. All right.